Are we good to get started? Okay, so Brandon asked me to do a talk on WebAssembly. I don't know why. Brandon, maybe you can explain why.
Sure, yeah. I think you may have mentioned it in passing or something, and I was like, I'd love to learn more about that without having to put in a lot of effort. Hey, Kevin, you want to put in some effort?
Great, yeah, I think that sounds about right. Yeah, so I don't have much background in this. My background in WebAssembly is essentially I shared a link to some really cool like fluid physics demonstration in it, and I think that's where it started. I've done a little bit with Rust and compiling WebAssembly before that, like a tiny bit, less than I needed to do for this. So if anybody has any questions, I'd probably say it will be great questions, and they won't be answered during this. But feel free to ask anyway, so we can I don't know, maybe write them down or outsource them. Yeah, so in I guess just over the last couple of years, WebAssembly has become kind of an official second language. And you might notice a little footnote there, and it's mostly official because it is not supported in Internet Explorer. Yeah, right? So I think the biggest hope I have for WebAssembly is that it takes off and helps kill IE for good. But anyways, let's start. So basically, there were a lot of different groups and engineers over the last decade or so that have been trying to get near-native performance in the browser, and who've tried other strategies for coming up with like a kind of a heightened security model for running untrusted code. So we're gonna kind of look at a few different questions, like what's the background, why they make a new standard, and all those other crappy questions you can see right there. What? It's Wasm. Yeah, we'll get into that one. So I'm going to preface this history with saying I am not a front-end developer. Thankfully for anybody who uses a Rocket app, I no longer write JavaScript. So please correct me if I'm wrong at any point of this brief history. That started with static text a long time ago in the simple days. So yeah, in the mid-90s, they created JavaScript at, was it Netscape, I think? Just to add some interactivity, like basic interactivity. And there weren't really like really high aspirations for it. It's just, hey, we need a little bit of interactivity, let's do it then. And then it just was sort of there, and the JavaScript was improved, and performance like it did climb upward over the next decade, but it was never really one of the driving goals for it, because people thought Java applets would be how we make apps in the browser. Thankfully, Google had really invested in JavaScript because they put out Gmail and Google Maps, and they were just starting to build more apps in JavaScript, which saved us because they decided to create a just-in-time compiler for JS as part of V8 in 2008. It was kind of an inflection point in the history of JavaScript performance.
That's a dumb question.
Yes.
What's the just-in-time compiler?
So right up to that point, JavaScript was really good. Every time it reached a new statement, it would, like in the moment, compile it to the machine code and execute it. And it didn't matter if you called the same function 10 times; it would continue to interpret it.
It's basically like it's written in a language that your computer can't actually execute. So when you go to execute it, that's as opposed to like C, where you're going to compile it down to something that.
Sounds like you're describing what interpreting is.
Just in time.
There's interpreting, which does have to obviously compile down the machine code. It's happening like as it's executing a statement, and it does it every time for that statement. And yeah, it's like it's different from ahead of time, like AOT compiling, like you do for things like that. Yeah, where you compile it for a specific machine, like a specific target platform. But so in this case, when interpreting it, the browser would compile it for whatever platform it's working on. So just-in-time compilation, it's sort of a hybrid approach where it still starts with this interpreted thing, but it keeps track of how it's compiling the code and how the code itself is being called. And so that it can start to say, okay, this thing's always being called with ints. I'm going to compile it a little bit differently than I would in the moment, because I know it's being called in, so I'm gonna compile it in a different way that's actually more performant. And so it's way over my head, and I linked to a great article in there. So Lynn Clark is an engineer at Mozilla, and she's like a phenomenal writer, who also has like pretty fun cartoons and all that stuff. She writes a lot about JavaScript and WebAssembly.
Some of those cartoons, man. I'm gonna learn so much.
But so this radically increased the speed at which we could run JavaScript, because it started with Google when other browser vendors started introducing their own compilers that would sort of kind of keep track of what they call hot paths and perform additional optimizations on them as it's going through the code. But Google's like, that's not enough. We want to be able to have like we want to be able to skip that whole just-in-time thing and have like actual ahead-of-time compile that's even more optimized. But it's hard to do that because there's tons of target platforms. Not everybody's on Windows. So they developed this thing for Chrome called Portable Native Client, or Pinnacle. And it only was ever in Chrome, and it was really only a prototype, but it was basically like, hey, we can compile for like this generic platform that we've created, and we can do all of the optimizations we need ahead of time, so we don't need to observe the code as it's running or anything like that. And we know these things are only going to be called certain types, so there's a lot more optimizations they were able to do. And kind of roughly at the same time, Mozilla was working on ASM.js, which was not really a separate standalone VM or anything running in a browser. It was really just trying to compile C or C++ to what they called like a subset of JavaScript. And there were ways that they could define, like compile to certain types of JavaScript functions that would leverage the just-in-time optimization cycles. So there would be lots of like coercions to or something like that. So and that would be happening in JavaScript, but everything would require an int. So then the optimizer could just kick in and compile it, and it just sort of worked better than that. And they also tried a strategy of skipping the garbage collector, because they would start to use these built-in arrays to treat as if it was like internal memory. And they could allocate a lot less on the heap by doing that, so relieving a lot of the pressure on the GC. And strangely enough, a couple years later, a lot of engineers from the Big Four started working together on a new standard that was built off of these technologies, because they identified limitations and they thought they had kind of a good working path for moving forward. And I might mention the WebAssembly working group at some point, and it's basically these engineers who are designing the standard and the implementations around it. And within a couple of years, they had finished the spec, and all the major browsers had actually finished implementations and shipped them like outside of feature flags by the end of 2017. So I think around November, in WebAssembly was live, except in IE again, which will never change. So why did they do a new standard instead of continuing to work on the JavaScript VM? So here is a quote from like a really cool white paper that they released a couple years ago. That was a lot of it was just describing the semantics of the language, which is over my head because I'm not a mathematician. But they also sort of talk about the barriers to greater efficiency as well as security of code. And I don't need to really read that. So the just-in-time compiler was great. Like we mentioned, it was basically like a 10x increase in execution speed, but there are a number of steps to it that actually prevent much more significant gains. And beyond that, like the JavaScript source files, whether it's JavaScript or even ASM.js, they need to be parsed into an AST, like a syntax tree, and that's not a fast process, especially on mobile. Like even moderate apps can take 30 seconds, and unless you're at my last job where we had a reasonably small app and it was still 60-second load because of bundle sizes. So that was great. But beyond that, like the just-in-time optimization required this sort of cyclical compilation and recompilation because it needs to continually monitor how everything is being executed. Like we mentioned, that it might observe that a function is always called with int, so it compiles its more optimized version that works with ints. But 300 calls later, it notices it gets past a string. It basically has to question its assertions that it made when it optimized it in the first place. And there's different levels. There's like baseline optimization and several above that, where it kind of just moves functions up and down these tiers as it observes how they perform. And it's always storing different versions of these things. So it's not only is it adding a lot of runtime to the call that's being made, it's like increasing the memory too. And ASM.js was great, but it was hitting a point where different implementations were adding optimizations to improve its performance, but that also tied it to those browsers that had optimizations to perform as well as it did. So that working group looked at this and like, we really can't work around these. This is just the nature of it. It got us a lot of speed, but it can't get us much farther. And additionally, we talked about this idea of untrusted code, and the browser sandboxed. They really can't access the file system or like the host system at all, but it still doesn't have any additional protections around running like third-party libraries. You can import anything in your JavaScript, and it has access to all the web APIs. And this is a really contrived example, but these 13,000 characters right here are sending a fetch request to an external website. And so there are a lot, and this is pretty contrived, and there are a lot of ways around that. Like, you can load a library and you have no idea what it's actually doing. That stuff's very difficult to audit. So they came up with a mission statement, and it's not very useful of a mission statement for any third party. And that's basically how the WebAssembly.org website is, and that's why Lynn Clark's articles, including the cartoon intro to WebAssembly, are necessary to understand kind of the inspiration for a lot of it and what they're actually doing. But basically, they wanted to develop a new format that didn't require the same kind of parsing, that could be compiled, didn't need garbage collection, and they kept talking about executing at native speed. And one of the goals was to be able to do that by way of like bypassing all these JIT compilers. So what is Wasm? There's lots of abbreviations and contractions all over the place. But at its core, in 2017, they released what was the MVP at the time. They decided that rather than have a big release, they wanted to have just this minimum thing and then build on it over time, which was definitely great for getting it out into the world. The first release included this idea of an abstract stack machine. It's saying that we're going to try to target this this conceptual machine that has a very limited instruction set that should be common and supported across every platform that we want to be supported on. And in the process, they had introduced this idea of two file formats, like this bytecode module that would be loaded directly, and then a textual representation that's actually human readable. And we'll get into why that's important in just a second. But one of the other more abstract things as part of the MVPs, they wanted to make sure that the design would be embeddable and portable. And it's and for non-browser applications was something they called out, which was interesting given that it started with the browser. And this abstract stack machine, it's not actually a different VM, it's just sort of this conceptual thing that the browser can then convert to actual machine instructions for whatever platform it's running on. So the biggest thing about WebAssembly is this idea of a module. And this is, there are a few really important factors on it. One, it's that it's embedded. It lives inside of a host, and in the case of the browser, it's only interactive via like the JavaScript VM. the JavaScript loads it, creates it, and calls functions off of it. Another big thing is that these binary modules they are even more sandboxed than JavaScript. They can call their internal instructions, any functions defined within the module, or something specifically imported into the module from the host. And one big implication of this is that WebAssembly modules don't have DOM access. They don't have access to any of the other web APIs. They can't make requests outside unless some ability is imported by the JavaScript host. So we'll talk a little bit more about that too. But and kind of following up where ASM.js was going, they introduced this idea of linear memory, and it meant that if a module wanted to store anything off the stack, it would have to use this byte array to access. It wouldn't interact with the garbage collector, but it also wouldn't be able to reach outside of these very narrow memory bounds. So these modules weren't intended to be handwritten either. Just like how Pinnacle and ASM.js started as compile targets, that's how WebAssembly was always meant to be. And it started as C and C++, but I think thankfully for the rest of the world, the Rust community has really embraced it, and they have developed pretty big advanced tool chains around WebAssembly already. But as mentioned, there's also textual formats, and you can handwrite it and compile it down to a binary module. As highlighted, probably one of the most important things about this is it's bidirectional. You can take a binary module and convert it back into a text representation. So unlike system binaries that you install, you can always open these things up and always see what's happening in them. So one implication of that is, obviously any business logic you have is not hidden. If somebody downloads your module, they can open it up and look at it. It's gonna look a mess, but
What language would it be in then?
we'll see. That it will be in a .wat file.
Wet.
It'll be a WAT file.
So human readable, but barely.
Yes. So this is an example of a WAT module. You could write this, you can compile this, and you can execute it in browser, and it works. So there's a very limited set of instructions. We'll talk about there's also limited types, but some of this is pretty readable, right? I mean, that's the minimum amount you need to define a couple functions and export them to the host.
Better than Perl.
That's
Shots fired.
Exactly.
Anyone?
So the weird thing is you might notice that there's a couple different formats. There's two functions that do addition, and they're written totally differently. And it ties into this idea that WebAssembly is conceived of as a stack machine, where you pop arguments onto a stack and then call a function that will, or where you push them on the stack and then call a function that will pop them off and do stuff. For when you handwrite it, you can write it like a normal function. This is, I mean, for our purposes, we don't really need to worry about that. But so that is what it would look like if you.
Yeah, it's like some intermediary
Yeah.
language.
I didn't write any, but unlike other lower level bytecodes, it actually has looping and conditionals and stuff built in. But
Better than assembly.
yeah, but it's so ugly and annoying that I didn't want to write it by hand.
It's better than assembly and Perl so far.
So it's only good for numbers right now. Cool, and it has distinct concept of 64-bit and 32-bit integers, unlike JavaScript. But there's actually no distinction between signed numbers. It's just it depends on what instruction you call them on. That really doesn't matter for us since we're only rewriting it by hand. But the implication of this is that you can only pass numbers into these functions, and you can only return numbers from Wasm functions, either to within a Wasm module or back to JavaScript.
You add your own types.
No. Nope. And so anything more complex than a number requires a lot of song and dance. Like trying to convert, so like for instance, if you want to do a string, you have to have a set of linear memory set aside, you have to marshal the string to bytes, and you have to pass pointers around. So it's very unpleasant.
Artisanally crafted string.
Sorry. Those strings are UTM encoded. But yeah, so like anything that compiles down to the Wasm module should have facilities for generating that kind of cool code. But there are still obviously the performance implications around it. Like the issues with WebAssembly, there's a lot of work being done on reference types right now. So I don't know.
What is that mean?
It means you will actually be able to pass in JavaScript objects. And yeah, so it's going to open up. I don't know if you'll be able to define custom types at all, but you'll be like you should be able to pass in JavaScript objects, references to DOM elements, things like that.
Yeah, well, it must open it up too, because you'd have since by reference, you'd have a pointer to that DOM element, which is not an integer.
It's a bunch of integers when you get down to it.
Before they do some arrays stuff, yeah.
There are some great docs around this that are way above my head.
I'm scared.
Yeah.
You just likewise add that DOM element to another DOM element.
That's the future.
Just like the DOM elements.
And now we don't really need to worry about the linear memory much because we don't manage it manually. It's basically like every module can opt to say it needs like a stretch of memory that is like X number of pages wide, and a page is just 64 kilobytes.
But you didn't do that in your example, though.
I actually will show that in actually, yeah. That last example only was pushing and popping things from the stack, so it didn't need it, any memory. But the cool thing is you can actually export and import linear memories between modules, which kind of helps open it up a little bit. But if you wanted to declare, if you actually wanted to use an internal linear memory object,
You asked for one memory.
yes. So that's assigning like this 64 kilobyte block of contiguous memory. But you have to do this song and dance note using the number type to store it, and to even be able to use like the literals, you have to say this is a 32-bit cost. Yeah, it's pretty fun.
How do you get rid of it?
Get rid of what?
So normally, like in a low-level language, you also have to deallocate that memory.
Right.
I think so. That would be allocated whenever the module is instantiated by the host.
Yeah.
And then I guess whenever it gets cleaned up in the host, then it would just be deallocated.
Yes.
So like this, the WebAssembly module,
Weird.
well, yeah. I don't know really how to details on it, but I'm assuming that's like when we actually operate on this thing as if it was a JavaScript object, at some point when we no longer need it, I think that the JavaScript will be able to clean up.
Yeah, that's something that we would be able to do, I think.
So this is already looking pretty ugly. And it's pretty useless if you can't actually load them. They're really easy to load if you do like a script type module, which again, not IE. Not that that's that sad thing. But to use them now, you have to do this little song and dance where you asynchronously fetch it, and then you have to create a buffer, like an array buffer from the response, and then you have to instantiate the module. And then once you're down in that last callback right there, you have this object that has instance, and that instance has like imports. Oh, sorry. On that line, on line 10 where you're doing the instantiate, right now it's only passing the buffer to it, but you could optionally specify like the imports. Like this is where you would tell the module what imports it's allowed to have. And so like if I define a module like a JavaScript function, I would import that during that step. And then
But you can't yet.
no, you can do that.
Oh, you can't.
Yeah, I just didn't write a function that took anything imports. You can import JavaScript functions right now.
Wait, what was the difference between that and what you were saying before with the reference work? You're saying you would just be able to reference JavaScript
I think,
functions instead of having to like copy them?
I think it's JavaScript. Yeah, I don't think it would copy that, but I think it's, useful for JavaScript functions that deal with numbers. I don't think you can actually do anything with this. It's a good question. I don't play that. I don't know.
Just break it.
Yeah, that's pretty nice. But yeah, so once it's instantiated, you can just treat it like this JavaScript object that has methods on it. And I actually did have to run this in the browser to make sure that I was doing my my linear memory thing right. But yeah, thankfully it does return 123 once you set it. It's delightful. So is it actually faster? So they've talked about how they want a near native performance, and benchmarks are pretty all over the place depending on what, like the amount of code being run and what tasks are being run. So the answer is no, it's not near native yet. I think it's closer than people thought it might be at this point, but it's not there yet. It does generally outperform JavaScript and even ASM.js when it's optimized. And plus, we have 64-bit integers, unless we want to return them from, unless we return them with JavaScript and it's a type error, because it won't take them. But originally, the different browsers had pretty drastically different performance with WebAssembly, like Chrome, and basically everything was generally slower than JavaScript, and then Firefox was much faster. But the other ones have started to catch up. And in general, there's a couple of asterisks. There's an asterisk when it says generally outperforms. It's basically referring to computational things. And so that it's noticeably better than even ASM.js on something that's optimized for it. So yeah, it's great for computational tasks, but right now we don't want to do anything with anything more complex. And let's not talk about that. So I was really curious to see if I could notice a performance difference. So I wrote a game of life demo in JavaScript and WebAssembly. And I don't know how well this is going to work. So we'll check the JavaScript one first. Let's see. So right now we just have this little game board that's playing, and we can kind of resize it as we go. Say, that's not what I meant to do. Oh, so it works pretty well. And it's fine.
Can I? Okay.
Yes.
What is the game of life like?
So I didn't know.
I was like the thing you spin the wheel and then put the little people in the
This is
more than 4 kids.
This is The Sims, didn't you know? So Conway's Game of Life is this, I actually don't even know where it's from, but it's this idea that you have a grid, and every spot on the grid either lives or dies at the end of each round. And whether it lives or dies is determined by like a very narrow set of rules, like how many live neighbors it has, how many dead neighbors it has.
Cool.
And so basically it's like only a few rules. But it's pretty useful for things like this because you can see, because it's just like lots of data that it has to kind of compare. Cool. So let's look at a size that's 512 by 256. And it's already starting to get kind of slow. But I'm going to open up the performance right here. Okay, so it looks like we're averaging about 5 to 6 frames per second. And you can actually start to see little dips periodically with the JavaScript garbage collectors kicking in. Let's actually turn off the rendering. And so right now, it's not rendering anything, but it's still doing like the round by round calculations. And so that actually bumped us up to like 12 frames per second, roughly. And it's still seeing like lots of these little spikes that are pressure on the garbage collector. So I forget what we're getting, like 6 when it's rendering, like 12 to 16. Speed up to this. Okay. So here's the I don't remember if it was 2 or 1. 1+1, okay. So I start playing that one. And so with rendering to the canvas, it's not noticeably different at this size. It's like 7 to 8. Let's turn off the render right now. As we see, like the average is already starting to hit up to 60 right there. Yeah. So when we turned off rendering in the JavaScript one, the max frame rate it had was roughly 30, and then that was 60. So a lot of the difference, like a lot of the explanation for there not being much of a difference when it was rendering is calls to the canvas. So that was useful because it really shows like when you see huge performance gains and when you don't. And when there's a lot of interacting with the DOM, you're not gonna get huge gains by switching to WebAssembly. But if you have heavy computational tasks, you could offload that to just like a quick little module, and it'll be radically faster. If they're running the full time, I should pause that. Let's see. So those are pretty fun to make. I actually had no idea what kind of difference I expected to see. Let's got a couple of other fun things people made. So this one's not going to look great over WebEx because it's going to be a little choppy. But so this one is like a soft body physics demo, and you can basically click and drag this little body around, and it's just entirely too much fun. Do you want to confirm that it's quite a soft body? It's quite a soft body. Sounds pretty fun because it's cool to have like the ability to do these little physics simulations. Epic released one. This thing called Zengo a little while ago, which actually I think is like 300 megs. So this might take a little while.
Is anybody like? Have there been any like thoughts or talks about like using something like this to like distribute workloads? Like almost like thinking like, remember I was like SETI at home?
Yes.
Yeah. Where like you could like.
Oh, I think there's. And again, this is much smoother on my actual computer. I was excited to open this up. I hadn't looked at this in a while.
What's happening?
Yeah, if anybody wants to actually look.
Whoa.
I haven't looked at this in a while. The last time I looked at this, it was choppy.
Yeah.
But yeah, so it actually gives you like different scenes you can play with. Let's go to Cherry Tree. So to the Cherry Tree.
How is that being rendered with?
WebGL, right?
Yeah.
Okay.
Which is also accelerated.
Actually,
There are sorry.
how is this like execute? This is on a like distributing like
Well,
workload or something?
Like I don't
Does
know.
it run on the same thread, or does it like have its own thread? Can you run like? Yeah.
It doesn't run in a different thread by default.
Okay.
But you can look at it, you just see workers.
Yeah. Right.
Okay. So
Interesting.
Yeah, so do they have a defined like threading model?
Well,
threading is on the. I mean, you could do it through JavaScript, like opening up a JavaScript thread and
Yeah.
and then instantiating a module. Threading is like in WebAssembly, something like they're actually working right now.
Okay.
That's like we talked about how it was initially they wanted this MVP, and then do incremental additions to it. Like there's this massive post MVP roadmap that they have, and threading is one of the things that I think is actually most actively worked on right now.
Strings.
You don't need strings.
Dude, a string is just a bunch of numbers.
Yeah,
You need strings.
just be a hipster. Like use numbers and drink your IPA. I don't know. I've seen this a few times, and it's been interesting for me. Like the last time I looked at this, it was choppy, and I know it was choppy for a bit in WebEx, but I can post it in Slack and you can play with it. Oh, I stopped sharing. That's not what I meant to do. Some guy,
Pretty stable.
Okay. Yeah, how do we get out of this full screen? There you go. Cool. Alright. That's pretty fun. That's a little bit cooler than a game of life.
I thought your game of life was pretty cool.
Thanks. Still think the blob is the best though. And it's funny, I was trying to find the demo I posted in Slack that started this whole thing and I couldn't. Unfortunately. Because there's like another I think soft body physics example, but blob is more fun anyways. So is anybody actually using this right now?
Figment's using it?
Damn it, I'm supposed to present, you weren't supposed to see that yet. So is can anybody guess who might be using this? Adam.
Figma.
How'd you know? Figma is in fact using WebAssembly.
An incredible intuition.
They were, Figma's app is actually, like, I think C++, and they were originally compiling it down to ASM.js, but they switched to WebAssembly. And like, if you look at that first link at the bottom, they noticed that it cut their load time by like a factor, or like cut it to a third of what it was when it was just ASM.js, and that's.
Is there like a new, what is Figma?
Figma is a tool that like our designers use.
Got it.
At least
I'm
someone
wondering.
Yeah, I had no idea.
Dan's a big fan. He did a talk on it a little while back. It's like, imagine an infinite canvas where you can just like mock up things, zoom in and out.
It's really
It's
easy.
like
to polish.
sketch kind of.
Yeah. It also performs well. It looks 3 times faster now. And like I don't think they've posted much about anything in those with performance other than load times. But and again, like the big thing about the load time is that there's no parsing to a tree and doing any of that before it can even execute anything. And actually, I forgot to touch on it, but one of the reasons the load time is so good isn't just because it's not being parsed into an abstract syntax tree. It's actually because WebAssembly was designed to allow streaming compilation. And the compilers that are in the browsers are, I think now they're able to compile it faster than it's even loaded. So it's like the compiling these to the machine code is not even a bottleneck anymore.
So the Wasm file is actually just like a binary syntax tree, right? So it's not really ready to execute.
It's a set of like binary, like it's a binary set of instructions.
Okay, but it still needs to be compiled like one last time.
Yeah, exactly. And so then the browser's taking that and compiling it to like the machine code. Like that binary is basically like the lowest common denominator of what can run on any platform. So Figma's using it. They converted their online app to WebAssembly and cut load time. Autodesk actually took AutoCAD and compiled it to WebAssembly and are now hosting it in AutoWeb. Which I'd be curious to play with because it was a horrible
I don't know what they're pointing at it though. Like Figma's using it. It's like, okay, where? You know, like God help anyone if they have to use WebAssembly, like they have to, like God help you all.
Wait, what do you mean?
It just like seems like the point where you need these performance gains and you can't get them other ways.
Yeah.
God help you. Like that's what I mean. So it's crazy that Figma's doing it. Like I just wonder where. You know, 'cause we've seen tools like that before, and like I have noticed that Figma is remarkably fast considering like, oh, I want to zoom out and I want to look at this thing like way over here, and like generally that stuff works really quickly, but that still is like very rendering.
Mostly for load time.
It's-
Load time, right?
Yeah, maybe. I don't know.
Yeah, I think they were already getting good performance from ASM.js, but it was still like the initial load they didn't like. I believe. I don't know.
It should like your first interaction should be faster rate because it's got streaming compilation,
Yeah.
and then it's just a smaller format too, so you're not sending it much over.
Yeah.
Yeah. It's ready. Wow. Do you want to finish this one?
I'm just thinking about you said it's binary, right? So
Yeah. So so Autodesk now has AutoCAD and web. Unity, for anybody who knows like about game development, like Unity is this kind of cross-platform game. I think it's cross-platform. Okay, cool. Yeah, they have a web player that actually I don't remember what it compiled to. They switched over to WebAssembly initially, and Google Earth was originally in the browser, but it was based off of their Pinnacle tech, so it only works in Chrome. But they switched over to WebAssembly, so now everybody has Google Earth. Does anybody even use it anymore?
It's a fun toy.
Yeah, so there's starting to be people who use it. Yeah, you made a good point about like, God help anybody who needs those performance gains and can't get them in any other way. What really stuck out to me with WebAssembly is that it's this great tech to really bump up this, like your performance when you're doing processing, obviously. And it's going to continue to get better and have more of a wider appeal in the browser when it gets like a number of features that are on the roadmap. Honestly, the most interesting thing to me is their work on non-browser hosts. Because this whole idea of like interaction by permission breaks, or it doesn't break, it's very against typical security models. So thinking about installing desktop apps on your computer, everything we install is basically this black box of untrusted code that we hope is not doing anything malicious. And even app stores, like stuff on Apple's App Store, are malicious, and they can't keep ahead of it. So one of the coolest things is that there's also work on what's known as the WebAssembly system interface, and that's, I think it's a specification. And what that would do is start defining ways of setting up hosts and runtimes for systems that can take WebAssembly, but that have more interaction with your local system than the browser does. So like honestly, to me, I think this is more exciting than what it gives us in the browser, because it just opens up completely new possibilities for how we can start to secure ourselves from external. Yeah, there's a lot of great reading on it. None of it comes from webassembly.org. Most of it is from Mozilla, especially Lynn Clark, all of the cartoons. But yeah, so there's this list of like everything that's post MVP, and threads are on there. And then she even did this cartoon skill tree with some of the original. Luke Wagner was one of the original people on the working group. And so she's like, let's think about WebAssembly, where it is and where it's going, in the form of like a skill tree or like a role playing. And so she goes through these different areas and says, we have and what we would need for something to be good for a specific use case, and then she kind of ranks at the end of each section, like where they are. So right here, making use of modern hardware, like native threading to WebAssembly is almost there. Load time improvements, like streaming compilation is almost there. I might be wrong, but I think only Firefox has streaming compilation right now. And last I tried it didn't work. Sorry, turned it off. But so this is heavily under development right now. And again, nobody writes this by hand unless they're masochists. And Rust is a wonderful way to get involved with it, because it's Rust was never designed for web developers, but the web world has taken it and ran with it. Not just on the server side, but and I think a lot of it has to do with them both being like sponsored by Mozilla primarily. But Rust is a great entry point into WebAssembly, and it's arguably much more fun than C or C++.
Did you write your game of life with Rust and compile it down?
That is a great question. Let's look. I don't remember where I am. Let's see. So the answer is yes.
You don't have Vim, alias the Vim?
I don't. I know, it's embarrassing. So in my Rust and Wasm version of Game of Life, there's still a lot of JavaScript going on. And that's like basically it has to handle all of the animation frames. It has to handle like writing to the page, and I mean some of this is handling those controls, but it even has to define like how to render it. And the rendering is particularly fun because you have to get a pointer to a spot in the memory, and then you have to create this new. Yeah, it's pretty messy. And you have to just. So it's pretty gross, but Yeah, in terms of the actual the universe itself, I just did air quotes. Watching WebEx can see it. Yeah, like all the game logic itself is Rust. Because Rust is fun. Universe. Universe. Yeah, that's all I got.
Is the game of life two-dimensional, or is it n-dimensional? Can you like do n-dimensional implementations of it?
The rules are pretty simple, they should expand.
Right.
Yeah.
Yeah. I just didn't know if that the generic implementation is.
Generic
I
was
look forward to your next lunch and learn on 3D.
Yes. next week, right? Yeah, no, it's just 2D, but I'm sure someone's done it in 3D. Yeah.
Good stuff.
Thank you.
Sweet.
Thanks.
Thanks, Kevin.
Study at home. Except for like the protein folding things, like those would totally benefit from this. So yeah, I think you're right. It'd be like so much faster.
So somebody did actually
Chrome tabs.
Yeah.
somebody did actually use a Wasm module and injected it somewhere to do a lot of Bitcoin mining on people's browsers. So that was fun.
Oh wow.
But
I just realized Study at home actually is running like native code anyway.
But like this is
Oh, and do it like in the browser.
yeah, it's an interesting distribution model.
Sure. Yeah, right, you don't even need to download and install anything, you just put it on the website. That's true.
Maybe they're like, why is my CPU? That's great.
Yeah.
Yeah.